In this video, we will talk about the Poisson ratio and also some important terminologies related to the stress and strain diagram. So to understand the Poisson ratio, so let's take an example of a rubber strip. So when we pull this strip in a longitudinal direction, the strip will elongate in longitudinal direction and it will contract in a lateral direction. So the strain developed in lateral direction is known as lateral strain, and when the strain develops in longitudinal direction, it is known as a longitudinal strain. So when a sample of material is stretched, like what I have mentioned previously, in one direction, it tends to get thinner in the lateral direction. And if a sample is compressed in one direction, it tends to get thicker in the lateral direction. So we can define Poisson ratio as a measure of the amount by which a solid spread out sideways under the action of a load from above. And it can be defined as a lateral strain divided by a vertical strain, and it is dimensionless. And the symbol for a Poisson ratio is nu, like what I show you in the slide here. This is the symbol for a Poisson ratio. So now I want to show you how I want to show you the calculation of a Poisson ratio example. In this question, we are given that a steel rod having a modulus of elasticity equivalent to 200 gigapascal, and given that the Poisson ratio equals to 0.3, and the diameter of the tension rod is equals to 15 millimeter, and now we want to determine the change in diameter of a rod. So let's say that we apply tension to it. We can say this tension rod, it may be a member of a truss, part of something, some sort of a tension rod, something like that. And in the inside, we have only one internal loading. We only have one internal loading, and we only have an axial loading, means that they are no bending, no torsion, and no shear, and we only have a normal force. And using an equilibrium equation, the only one that is applicable here is force in the horizontal equals to 0. Force in the horizontal equals to 0. And the normal force is equals to plus 20 kilonewton. Normal force is equivalent to plus 20 kilonewton, indicating that we are in tension. And now we want to calculate the normal stress associated with this internal loading. And stress equals to normal force divided by area, and in this case, the normal force equals to 220 kilonewton divided by the area, and we will get 0.1132 kilonewton per millimeter squared, or a gigapascal. And now, using Hooke's law, we can relate the stress to the strain. We can relate the stress to the strain, and we can just use the material property that we have. And the normal strain parallel to the loading equals to the normal strain parallel to the loading equals to the normal stress divided by E, or the modulus of elasticity, that is 0.1132 gigapascal divided by 200 gigapascal, and we got and this is the value that we get, 5.66 times 10 to the power of -4. And finally, we want to calculate the lateral strain. This is the equation that we use. The Poisson ratio equals to negative lateral strain divided by strain at a longitudinal. And given that the nu equals to 0.3, so now we can calculate the lateral strain equals to negative 0.3 times 5.66 times 10 to the power of negative 4. And this is the value that we get. We get the value of lateral strain equals to 1.698 times 10 to the power of negative 4 millimeter per millimeter, meaning that the value is dimensionless. And finally, we can find the change in the diameter. The lateral strain equals to change in diameter divided by the original diameter, as what we can see in the figure here. And the value of lateral strain equals to negative 0.1698 times 10 to the power of negative 4, like what we have calculated previously. And from here, we can rearrange the equation. We can find the change in diameter. Just arrange the equation. And this is how we can calculate the change in diameter equals to negative 1.698 times 10 to the power of negative 4 times 15 millimeter. And this is the value of a change in the diameter, that is equal to 2.574 times 10 to the power of negative 3. So why do we have a negative sign here? Because we pull the rod in tension, so the diameter of the rod will be reduced or shrink when we apply a tension force to the rod. So here we have other common stress states. We have a biaxial tension, and we also have a hydrostatic compression. So when the tension and compression forces act in two directions along the x and y axis on a specimen simultaneously, it is called a biaxial tension compression, where the forces applied outward in opposing direction on two separate orthogonal axes. And we also have a hydrostatic compression that can be defined as a state of a stress in which the normal stresses acting on any plane are equal and where the shearing stresses do not exist in the material. And examples of a biaxial tension, here we have a pressurized tank, and for hydrostatic compression, the example for hydrostatic compression is a fish underwater, where the forces applied inward will create a triaxial compressive stress on the body of the fish, for example. And here are some important terminology related to a stress and strain diagram. First, we have stress and strain. That can be defined as a size-independent measure of load and displacement, respectively. And we also have a stiffness that can be defined as an ability of material to resist elastic deformation. And Young modulus, or E, is the measure of stiffness. And we also have resilience, or what we call as daya tahan in Malay. So resilience is the capacity of to absorb energy in the elastic region. And here we have the modulus of resilience that can be defined as the total elastic strain energy per unit volume for the area under the elastic portion of shear versus a strain diagram, like what we have here. So the area under the elastic region, is the modulus of resilience of that particular material. So resilient materials are used in a spring application. It is used in spring application, and they have a high yield stress and low modulus of elasticity. And now we have a yield strength that can be defined as the stress that required to produce a specific amount of a plastic deformation, usually taken as a 0.2% of the unstressed length. So here I show you again the stress and strain curve or diagram, and we have 1, 2, and 3 and 4 point here. So between point and 1 and 2, this is what we call as an elastic region, and the slope of this point 1 to point 2 is modulus of elasticity or Young modulus, and at around point 2 things start to fall over. Here we have linearity from point 1 to point 2, but after point 2 things started to change. We have reached the proportional limit where the slope has changed beyond this point, and at the point 3 we reach the yield strength, where the strength is starting to yield and the materials start to yielding the whole way across the region up here. So where do we can find the yield strength of this particular material? So to determine a yield strength, engineers standardize the method by pick one point in the yield region that specifically point to value along the strain axis here, and rather than taking a point and drawing it straight down, drawing it straight down. So what they do is they take a point at 0.2% strain. And why do they choose 0.2%? Why? Because lots of sample have values and data at a 0.2%, and instead of going up a vertical 90 degree, they follow a parallel line where that follow the same slope as our Young modulus here. So that is how we determine the yield strength of a material taken at the 0.2% of the unstressed length. And now we have ultimate tensile strength. So how can we define ultimate tensile strength? The ultimate tensile strength, often shortened to a tensile strength or ultimate strength, is the maximum stress that a material can withstand while being stretched or pulled before failing or breaking. And tensile strength is the opposite of a compressive. It is the opposite of a compressive strength, and the values can be quite different. And some materials will break sharply without deforming, and we call that as a brittle failure. If you can recall from what we have learned previously. And others, while more ductile, including most metals, will stretch some, and for particular materials such as rods or bars, shrink or neck at the point of a maximum stress as that area is stretched out. And then we have a fracture strength that can be defined as a stress or load fracture start to occur in a material. So the fracture point is the point of strain where the material physically separates. At this point, the strain reaches its maximum value and the material actually fractures, even though the corresponding stress may be less than the ultimate strength at this point, and ductile materials have a fracture strength lower than the ultimate tensile strength, or UTS, whereas in brittle materials the fracture strength is equivalent to the ultimate tensile strength. So as we can see in the figure here, this is the point where the materials will experience fracture. And then we have ductility, that can be defined as the ability of material to undergo plastic deformation without a fracture. And to calculate the percentage of elongation, this is the equation of how we can calculate the percentage of elongation. We can calculate the percentage of elongation by dividing the change in length divided by original length of that material times 100%. And from here, from the stress and strain diagram here, we can see that if the materials have a small percentage of elongation, means that materials, if brittle, where the the percentage of EL is less than 5%. And if that materials have a larger percentage of elongation, means that particular material is ductile, where the percentage of elongation is higher than 5%. And now, and then we have a modulus of toughness that can be defined as the ability of material to absorb energy in plastic deformation. It is defined as the amount of strain energy density, or the strain on a unit volume of material that a material can absorb, before it fracture. So material's modulus of toughness will vary depending on the material's ductility, and two materials with the same yield strength can vary greatly in their modulus of toughness if one of the materials is more ductile than the other, and the ductile material will stretch further and have a greater area under its stress strain curve. So here we have different toughness of different types of material. So we can see that for materials that display a small toughness, such as ceramic, it has a small number of area under the curve. And for larger materials that exhibit a larger toughness, for example, metals or PMC, it shows large area under the stress strain curve in the stress strain diagram. And here we have area under the curve for a smaller toughness material, such as unreinforced polymer.